have roots in Q. But we don't want to go to the complex numbers so that they have the roots. So we need to find something which is in between Q and C, so that we can study that polynomial and its roots inside that field. So what will essentially come out are called number fields, and you can just take them to be finite extensions of Q. Now, what we do in Q, we have the integers, and that is where number theory is born. So we need to do something very similar in K, but it actually turns out it is much more interesting or much more convenient to work with ideals than with actual elements. So you have integral ideals and fractional ideals in K, where the integral ideals are the analogs of integers, and very vaguely, very loosely, integral ideals are analogs of integers and fractional ideals are analogs of fractions. So for each integral ideal, you can associate something called the norm, which measures the size of the integral ideal, and we take a natural number m and we collect all the integral ideals of size m. We know that there are only finitely many of them, and we call that number as ak of m, where k is the number. Now this AKs of m are, if you look at each of this AKs of m individually, suppose you fix 10 and you consider AK of 10, and you take 11, you ask what is AK of 11. Now this is something very specific to that number. You need to know exactly what that K is, and you need to do all these things by hand. But as an analytic number theorist, I'm interested in the average of these AKs. So I will sum up the AKs up to a very large number. I will take AK of 1 plus AK of 2, etc., 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 to AK of 100, let's say, plus AK of 1000, and I will ask how the sum goes. And even more generally, I can consider AKs to the power L, and then I can take up to a large number X, and I can ask how the sum goes as X goes to infinity. Now, before I move forward, you are well within your rights to ask me, why should you bother? Why is this problem important? Well, the first answer that I can give you is that AKs of M are such very old objects, such well-studied objects, but we still don't know the answer to the earlier question that I posed for a very large family of cases. So we know the answer for some cases, which I will extend by the end of this talk, but still there are a lot more cases where you cannot estimate the sum with sufficient amount of precision or accuracy. So in that sense, this is interesting in that sense, because we do not know even such a simple enough question about such a classical object. And the next reason that I would like to give you is that it gives me an opportunity to talk about ordinal functions. Ordinal functions are so amazing that you can see for yourself how the analytic number theory and algebraic number theory have such a symbiotic relationship among themselves. You can take aspects of analytic number theory and you can take aspects of algebraic number theory and just combine them and you will get ordinal functions. So, but because of time constraints, I will not be able to give much details about ordinal functions, but I will only briefly mention them. But I'm available here, and I'm happy if any of you are interested in talking about ordinal functions. Okay, right. So first things first, we can as we have the Riemann zeta function for the Q, we have something called Dedekind zeta function for the field K, and they are and it is actually given by this series summation AK of m by m to the power s, where AKs of m were what we saw earlier. And so let us give this sum a name. Let us call it SL of x, S for sum. And okay, and this is known as the Lth moment of zeta k, and hence the title. Right. So when K is a Galois extension, Chandrasekharan and Good established asymptotics for the sum SL of x. So if K is Galois extension, what happens is that the AKs of P's and the AKs of M have very nice symmetries. because there is an action of the Galois group on the ideals, which will eventually imply certain nice results about this AKs of M. And you can use those results about the AKs of M and you can estimate the sums for when K is Galois. The first result, and if K is non-Galois, the best that you can do is you can show that summation AK square of M is double less than x log x to the power n minus 1. Here n will always be the degree of my extension of K over Q. And but this is, as we shall see, this is a very bad bound. So the second result actually predates the first result. The second result is actually due to Chandrasekhan and Narasimhan. They obtained this as a corollary to another result where they put the approximate function equation for certain L series, and they did not give much attention to results of this form. And later this was taken up by Chandrasekhan and Dutt. The second result was in 1963, and the first one is 1983. But they were only able to do it when K is Galois. And of course, so there are two major limitations to the second result. The first one being that you can only estimate the second moment, and the second limitation is that you only have an upper bound, so you do not have asymptotics. So to remedy this situation, first Fomenko and then Lu Guangzhou studied the next simplest case. So you know that every degree 2 extension is Galois, so you have nothing to do there. So you take a degree 3 extension, you take it to be non-Galois, and then you take the Galois closure, and suppose the Galois group is isomorphic to S3. That is the next simplest case that you can study this problem. And in that setting, they study the second and third moment. And yes, so this actual theorem which is on the slide is due to Lu, but a similar theorem was shown by Fomenko, whose error estimates were weaker. So what Lu did was to improve the error estimates. But again, we have a lot of things which we can ask for. The first thing is that they use the truth of something called the strong Artin conjecture, which is known on only on a handful of cases. You can literally count with your hand how many cases for this is known. And the second thing is they had to restrict very specifically what is the field and what is the Galois extension, and all those things they had to restrict very specifically. And the third flaw, I should say, is that they can estimate only the first and second moments. They don't know any asymptotics for summation AK to the fourth. So what my work, which I hope to present today, is in some sense improves their result, improves the family, or improves the family in many ways. In the first, we can estimate the moments for a larger class of number fields over Q. And the second is we can estimate the Lth moment for a very large family of fields. So in almost all cases, you can estimate every moment, and in some cases, you can estimate even moments. And this is in some sense explicit, explicit in the sense of a theoretical word, in that if you actually sit down to write down what is that exact polynomial, PL of log x, it will be very hard, but it is something which can be computed. But the delta is something which we can write very nicely. So the error estimate becomes weaker as the degree increases and as L increases, which is something that is expected. Okay, so another thing, this is in line with what we saw earlier, the results of Good and Lubav's. Okay, right. So the idea of the proof is you start with this L series, and it is not hard to show that the size of AKs of M is double less than M to the epsilon. So DL of S is absolutely convergent for L part of S bigger than 1 for every L. But the whole point and the reason why we need these additional hypotheses is to show that DL of S has an analytic continuation real part of s bigger than half, except for the high order pole at s equal to 1. So that pole is what is contributing to the main term, which is of the size x into some polynomial of log x, and the other estimates on certain integrals will give us the error. Right. So from here we can apply some standard techniques from analytic number theory to appear analysis. Right. Now, so these are the additional hypotheses that I would like to reinforce. So first, we assume that G can be written as a semi-direct product, where we have n semi-direct product H, and psi is an automorphism from H to the automorphisms of n. This is a very standard construct. This is a very standard construction in group theory, and so that is the first thing about the structure of G. The next thing that we assume is that n should have a normal subgroup which is stable under the action of H. So H is acting on n, with which you are constructing the semi-direct product, and n should have a normal subgroup n prime. So the reason why we need this is that we should be able to restrict the action of H to n prime and obtain n prime semi-direct product H. That should be well defined. And we make this assumption that if let us look at the setup that we have here. Have Q, and we have K. This is the number field that we are interested in, and then we have K prime, which is the Galois closure of K. Now, it is immediate from Galois theory that K prime is also Galois over K. Now, you take this as your G. You should be of the form n semi-direct product H. This I am calling it as G prime. The Galois would go here, and I want it to be equal to prime semi-direct product H. This is my setup. Now, in this setup, we can, since n prime is normal in n, we can give a group structure to n mod n prime, and I am calling that group as n double prime, and these are just some extra notations which is not that important. Okay, so what is important is that because of this structure that we have assumed on G, you can write every element of G as n1 into H. This is not exactly a product, as in, but we can identify every element in this form. So, right. So now I need to use a little bit of representation theory of G. So you take the trivial representation of G prime, which is the Galois group of K over K prime, and then you can induce it to a representation of G, and I am calling that representation as ρ1 and the corresponding character as psi. Now you have an H which is sitting inside G. Now this ρ2, this is another representation of H, which is actually the direct sum of all the reducible representations, or this is in fact the regular representation without the trivial representation. Okay, and we shall consider this as a representation of G via this projection from G mod n. So since G can be written as semi-direct product n times H, it follows that n is normal in G and G mod n is isomorphic. Yes, so these are the assumptions that we make. So for any two elements in H which are not the identity, we'll have NH1 double prime, which is a subgroup of all the fixed points of H1. So every element of H should fix the same subgroup inside N. The next thing is, so this is the ordinal function that I'm talking about. So ρ1 is a representation of G, ρ2 is a representation of G. There is something called ρ1 tensor ρ2, which is again another representation of G, and to that representation you can associate null function. this this involves some amount of classical theory. That is why I don't have time to go into the actual construction. But I make the assumption that that L series is entire. So this is called the Artin holomorphic conjecture, and even this is in fact not known in many cases, but this is weaker than the strong Artin conjecture that was initially assumed by or initially used by Fumiko. So in that sense, I can justify this assumption. I'm sorry. Lastly, this is some technical hypothesis which we need so that certain LCDs have integer powers and not fractions. Okay, again. So before I go into the proof, let me give you some examples as to show that this setup is not void. So the first case is if H is the trivial group, then we get back the result of illustrative method. We will have G prime is equal to G, and then K is equal to K prime, and K is in fact normal over Q. So normal and Galois are the same thing over Q because every extension is separable. Yes. Now, so this is one of the first improvements over the previous results. Is that if you take a diagonal, sorry, if you take an abelian group, then C2, which is the cyclic group of order 2, acts on n via inversion, and you can define this n semi-direct product C2 very naturally. And since n is abelian, you can choose n prime to be any subgroup of n because every subgroup is normal in n, and you will still have the action of C2 on that subgroup. So in that setup, whatever we are doing will work. And as a special case, if n is a cyclic group, we'll get the dihedral. Right. So we can do the same thing for symmetric group for n is bigger than 5. We can write Sn as an semi-direct product C2, and we can verify all those assumptions are true. And for n equal to 4, A4 is not simple. So we cannot, at the moment, it is not clear how to do it for S4, but we can do it for A4, and A4 we can, and yeah. So depending on the choice of n prime, you will be able to estimate every moment, or will only be able to estimate all moments. That is something very specific to A4. Now this is not an exhaustive list. You can find other groups and other instances where these all these conditions will hold. Right. And the inverse Galois problem is well known. So like you have groups, we have number fields. So that is the whole point of what we're doing, and it is known that we have number fields whose Galois groups are all the standard groups at this condition. Right. So now I'll just mention a few important ideas of the proof. I'm not going to the proof. Right. So we shall restrict to primes which are unramified in K. That means we are omitting some bad primes which are only finitely many. So I don't care about them because they don't affect the results much, except for a few constants that will occur here and there, but I don't care about much. So now AKs of M's are multiplicative, and therefore this series has an Euler product representation. Again, valid in certain half-plane stages of convergence, etc., etc. But the whole point is we can write this as an Euler product, where again the product of primes runs over the, okay, here the product runs over all primes, but without explicitly mentioning it, I shall restrict to primes which are unramified. Right. So yeah, you can. So remember, chi1 is the that's a character of rho 1, and for every prime p, there is something called the Frobenius element. All this is inside classical theory. I do not want to go into the details, but the takeaway message is that so you can choose this alpha of L and beta of L in such a way that this L series, you take the ordinal function attached to rho 1, and you take the ordinal function attached to rho 1 tensor rho 2, you raise it to the certain powers, this will have the following Euler product. So what this does is that when you take the quotient, the first term will not be there. The first coefficient will be 0. And the Euler product, now this the second Euler product that I'm mentioning, that is only over the unramified primes. For the ramified primes, we have to do something different, which I don't want to mention here. So the first term cancels out, and what you will get is an Euler product of this form. And because of that 2s in the P power, this is absolutely convergent for real part of s bigger than half. So you can call it UL of s, and we have this theorem. UL of s is this product of L series times something which is absolutely convergent for real part of s bigger than half. Now we know that L as rho 1 is L as rho 1 is actually in fact theta k. That is a standard result. L as rho 1 is in fact theta k, and we know it is valid everywhere in the complex plane except for s equal to 1. And the second L series is why we need to make that assumption that rho 1 tensor rho 2 is entire. And UL of s is just absolutely convergent. So now you can use the properties of L as rho 1 and L as rho 1 tensor. So there are some properties which are standard and well known. You can use those properties to estimate DL of s. So the whole point in this estimation is something called the Perron's formula. You can write SL of x as an integral involving DL of s with an error term, and then you can shift the line of integration appropriately and use these estimates, which are standard estimates, and then you can get the desired result. I don't want to get too much into it. Okay, so what can be improved? The first thing that can be improved is what are the additional hypotheses. So can we remove certain hypotheses, or can we increase the family that we have just proved? And the next thing that we can ask is, can we improve the error term? So delta is something which can, so delta will be in fact alpha of L, the alpha of L that we saw. I should not make a mistake. Yeah, delta is in fact 1 by alpha of L into theta 3 plus beta of L into theta 4 plus 2, where theta 3 and theta 4 are some constants coming from the subconvexity problem. Excuse me. So yes. So can we improve the delta? That is one of the questions that comes up, and the other question is, can we relax the additional hypotheses and prove something like this for a larger family? So this is the primary reference. It will appear in the Journal of Number Theory, and these are the other references. So yeah, the paper by Chandrasekhar and Good is third, and the paper by Chandrasekhar and Axel is fourth. And thank you.
Is there any questions? Yeah, so that you mentioned two theorems on Chandrasekhar. They did it for certain Galois groups, right? For instance, symmetric numbers.
No. So what is the difference between the first and second theorem is that the first theorem, your K has to be Galois over K.
Galois group has to be Sn.
No. So in the theorem of Chandrasekharan and Good, there is no assumption on the Galois group. They just assume that K has to be Galois over K. So wait, let me just get to the slide.
Next paper, what Drew and AD, they had some restriction.
So here, K is just the Galois extension of K. There is no restriction on the Galois, because then you have certain symmetries of AKs of P's, and once you have the symmetries on AKs of P's, you can get some symmetries on AKs of M because of this notion of multiplicativity. What Lu and Fomenko, what they did is that, okay, if your k is not normal over q, what is the simplest case? What is the next best case then? So they took a decreasing normal distribution. But it happened that somehow you need to bring in ordinal functions. Without that, you it is unclear how to handle this problem. Yes.
Trying to find a general condition over the Galois group in particular to get such results, or
Yes, in some sense, these two results are subsumed over what I've done.
yeah.
But yes, I guess the most general result will be to do it for any Galois. So yes, to answer your question, yes, but that is not the end goal.
But I lost over a comment. You said the examples in which this is possible. You said for that the inverse Galois proposition. So is that
Yes. No. So I mean, so
not for the theorem you presented? I'm saying, is that something that you desire?
okay, whatever conditions that I imposed was on the group G, but we can ask, do there exist number fields k and k prime such that k is sitting inside k prime and k prime has this group Galois group G? Yeah. I mean, does it make sense to consider that group? Yes. So that was what I meant by the inverse Galois.
Yeah, but initially we thought that we need to get some examples. No?
Yeah.
These conditions came because you wanted to prove that theorem.
Yes.
And then these were forced because of the whatever the results are known. But then you need to get some examples where really it happens. And actually, then we saw that many cases that
It actually turned out we were able to handle a lot of standard groups.
And I think we have not tried, as you pointed out, there are many other groups which one can just figure out, and this result will be true for that.
Tell me a bit more. What are the assumptions on the group? Can you recall?
So okay, this is so. First, I'm making some assumption on the structure of the group. Okay, I'll just go through. So first thing is we make the assumption that G is of this form, and we also need this. We need n prime to be normal. Okay, I mean if m is equal, then there is something proper normal subgroup, and we need an action of H on n prime, so that we have this sort of structure. So it is not that there is restriction in the Galois, we have restrictions on what number field k which we can choose. Not every subgroup of G will be of this form. Okay. Then what happens next is that we take n double prime, n1 n prime, and then we can identify the subgroup of n. Right. And since you have an action of H on n, we can say that we have an action of H on n. Right. So with respect to that action, we want every fixed point, every fixed subgroup to be the same. For every H. So this was the first thing that we want. So if you remember, there was a table on the slides, and all these assumptions were made so that that table has a mesh properties, so that we can get alpha L and beta L. Otherwise, anyway, so this was the first one. Second assumption was that LS rho1 rho2 is entire, rho1 tensor rho2 is entire. This is in some sense a serious assumption, I would say, but this is in fact expected out of the Lagrange transform. I would not say this. It is extremely unlikely that this will be disproved. It makes sense to make this assumption. And the third one, and, and there was some components condition. I don't exactly remember it right now. This was to make sure that the alpha L's and beta L's are integers, because you are dividing out by h, which is the size of capital H. And there is a freedom to what those labels can be. You can't remove any. Sorry? There is no freedom.
What values are desirable in that table, you can't remove any of these hypotheses.
Yes, yes. So this is like a cat and mouse game. You have to tweak your assumptions and. Okay. Any other questions? Anybody else? Or Vishwanathan have more questions?
That we can ask later.
Okay.
We're hungry for tea.
Okay. Any online participants? Okay. So Shubham, are you there?
So Krishna,
Yes, sir.
Ah, yeah. Fine. Good.
Yes, sir, I'm here.
yeah, what I think, Krishna, as Vishwanathan was telling, no, give these guys some problem. On this.
Yeah.
Find a group in this kind of conditions. Like you have chopped out few of the exercises.
Okay.
So-
Maybe we can talk about it.